Well, hi again, Mr. Bleecker here. We're going to get going with our next major topic, which is lipids in our study of nutrients. Now, with lipids, I want you to be thinking of fats and oils and waxes. And one that you may not have thought of, I want you to think of steroids. Usually, what comes to mind with steroids is testosterone and estrogen. That's so some of the more common ones you'll be thinking about. But I also want you to think about cholesterol, which, as it turns out, is also a steroid. So we've got a lot to do. Let's get to it. Click on biochemistry lessons there, which will bring you to this screen. And the material for lipids is here. The animation that will be really important is this one called triglyceride formation of lipids by removing water. Now, it's an interesting trick. We've already seen that by removing water, we can build things up, which we call condensation synthesis. Now, if we reintroduce water, we can break things down, which we call hydrolysis. The good news is you already saw that in the previous chapter when we were studying carbohydrates and monosaccharides, disaccharides, things like that. So you've already seen it. Let's go. Let's see what we've got. All right. And away we go. So lipids are a source of long-term energy storage, right? When you think salad dressing, oil-based salad dressing, that's sort of the first thing that'll come to mind. You might be thinking of things like cheese, right? With all the fat in the cheese, for example. You also see oils and fats in things like, well, mostly oils when you're thinking about plant material. Fats, you tend to think about sort of animal-based sources. And as I said, we'll be getting into the discussion of cholesterol and other steroids. Let's make that a little smaller. Okay, perfect. Now, you've probably heard it said that if you overconsume, your body will break things down with enzymes into simple components and restructure them, and that's absolutely true. An overconsumption of carbohydrates, for example, can lead to lipid formation. An overconsumption of protein can also lead to lipid formation. Lipids themselves are very energy rich. In fact, when you look at the energy that lipids can store, you'll be looking upwards of 9 calories per gram. And that's very, very high. Now, your body puts this away for a rainy day. And if you think back to Biology 11, there's one interesting creature on our planet that when it photosynthesizes, makes oil. It belongs to phylum Chrysophyta. It was the golden brown algae. You probably remember the little diatoms. They were kind of interesting. Sort of looked like this. Little crystal cases, and they lived inside of them like that. Now, diatoms can photosynthesize and produce lipids. Now, when you look at 9 calories a gram, you probably figured out why. If you want to reduce calories in your diet, don't eat the lipids. Carve the fat off your steak. Don't eat so many fatty meats. If you avoid meats, you can eat plant materials, right, which tend to have a little bit less lipid content. But lipids are what our bodies do to store energy for a rainy day. In fact, when you look at the function of lipids, it's not just energy storage in the body. There's a couple more things you should note here. Right? They're a cushion for our organs. That's a good thing, right? You don't want your organs compacting on one another. Now, excess amounts of lipids can create a lot of congestion down there, so it's a good idea to monitor your diet, for example. But when we think about what exactly lipids are, they're really another sort of source of carbon, hydrogen, and oxygen storage. And when they're broken down, they'll be broken down to little sort of chunks to be fed into the mitochondria. But it's nice that we've got this large storage area for these. Now, lipids themselves, in addition to cushioning our organs, all of our membranes are made up of a little sort of fatty layer that we call a phospholipid layer. And we'll talk about phospholipids later on, but you heard the lipid part there. Yeah, lipids are really important because they make up the skin of all of your cells. They formulate our hormones. And, of course, they're a source of energy. So fat and oil are probably two of the most natural ones coming to mind. And sometimes you hear these things called the neutral fats. What do they really mean? Well, when you look at lipids, you think about oil, for example, it doesn't mix with water at all. It's neutral. It's a non-polar molecule. Doesn't have a positively charged end, doesn't have a negatively charged end. And for that reason, it's not something that water will bond with because water is polar. So the two are sort of mutually exclusive. If you've ever whipped up salad dressing, you have to shake very hard just to get the water and the oil just to mix together. So first of all, we'll think of these fats and oils as being energy storage. And the rest we've kind of already mentioned, special lipids that'll make up the cell membrane, and ones that will formulate our hormones and our steroids, which help regulate our body processes. All right, so let's get to it. What is the subunit of a lipid? Well, it turns out it's this thing called glycerol and what we call fatty acids. Now, I'll explain what fatty acid means in a minute, but I think the best way to get this is to look at just what the heck that looks like as a molecule. Now, this is a very simple way of drawing it. In fact, many times when I go to draw it in class, I'll do just this. Draw the glycerol part, which is it starts out as an alcohol. Whenever you see OL, right, that's a dead giveaway that something's an alcohol. And often, when I draw a triglyceride, okay, think of tri. Why is it tri? Well, there's 3 fatty acids off to the side, right? So that's one way of helping you remember this. It's an interesting molecule. This is the basic structure that I would just show, with the glycerol and the 3 fatty acids like that. But there's a little bit more to it in how it comes together. So here's glycerol. Now, glycerol is a 3-carbon alcohol. So the alcohol portions are these little guys off to the side here. Don't need the carbon in there. There we go. And those side groups are very reactive. They're hydroxyl groups. Now, whenever you see them, it's like a dead giveaway that there's some chemistry is going to happen on that side. So glycerol itself is just waiting to react. To react with what? There's another side group that you'll see in what we call fatty acids, and it's called a carboxyl group. So what you're seeing here is basically a hydrocarbon chain, repeating hydrogen and carbon. But when you get on the end, this group here, carboxyl, is extremely reactive. Well, why? Well, you see one of these hanging off the side. And we often call that, it's the carboxyl group, we call it the acidic end. Now, the reason this is going to be called a fatty acid is because the acidic end is going to go through a reaction and it's going to form these fatty molecules. Interesting little way of remembering it. So the chemistry is we're producing something that is a fat, an oil, or a wax. So we often refer to these guys as being our fatty acids. All right, so here's where it comes up in detail, and I'll show you an animation of this in a minute. When you look at these end groups, you look at these hydroxyls here, you know that they're fairly reactive, and carboxyl groups, these guys, tend to be quite reactive. Well, it's because of this end here, that OH. In each case, what you're going to see is a reaction of these sort of dueling end pieces, and we saw this with the carbohydrates, where we'll get the release of water through condensation, or the older term, dehydration synthesis. Now, when we look at that, my girls love Angry Birds. When we look at this, we look at what's missing, and H2O has been removed really at each one of these stages here, at each one of these bonds. So the fatty acid, first, second, and third, I'll just write it there, have combined in a way to remove water, which is condensation synthesis. Now, if we take the glycerol, this guy here, and we hook up through three fatty acid molecules like that, those hydrocarbon chains that you see off the side, what we have is basically lipid storage. This whole piece is just the one little Lego part. Interesting. Zoom out. And it's all with the hydroxide ends and the removal of water. So I'm just going to pop out of AirPlay for just 1 second. There we go. And show you what this looks like sort of in an animated way. I'll just mute this. There we go. And
a glycerol molecule contains 3 hydroxyl groups.
Easy to see it coming together.
The hydroxyl groups can react with the carboxyl groups of 3 fatty acids.
There's your fatty acids.
This reaction forms 3 molecules of water
adjacent hydroxide groups.
And 1 molecule of triglyceride.
There is known as an ester. And sometimes people will oversimplify it, saying it's a carbon to oxygen to carbon bond. Really, we don't have to get into the specifics of esters, really at the grade 12 level too much. But esters tend to form between alcohol groups and acidic groups. So in this case, the acidic group, which is the carboxyl group, reacted with an adjacent hydroxyl group, or hydroxide. You can think of it that way. And with the removal of water, we got 3 ester bonds forming. Now, we had seen ester bonds form before. I didn't get into detail on it, but that happened as well in the formation of our disaccharides and polysaccharides. But it's a good little animation, and it's just as nice twice. This one's a little bit smaller.
Because the important part of what you're paying attention to here is the glycerol backbone as it's introduced to the fatty acids, the 3 fatty acids that are going to make up your triglyceride subunit. As they come together, this is called esterification. It's when the hydroxyl group of the glycerols bind with the carboxyl group of each adjacent or nearby fatty acid. Now, indicated if you look at the blue highlighting, what you get is the formation of water molecules, specifically 3, and that is enough to form 3 esters.
Glycerol separated from our fatty acids, and that's what's done when the body wants to make chunks of hydrocarbons. Remember that really the name of the game is to feed hydrocarbons, about 3 carbons at a time, into the mitochondria, like shoveling coal into an oven for the purpose of generating energy and running the processes of the cell. So, I'll just pop back into mirroring here, and we can get going. All right, now this diagram, you have my apologies. It was drawn so large that it didn't have room for this fatty acid right here. So, if you're paying attention at home, yes, there is a fatty acid missing from this region here. But the name of the game is a glycerol and 3 fatty acids gives you 1 triglyceride and 3 water molecules. True story. Just a second here. Every now and then I get that where my page won't load. There we go. Excellent. So when you look at a triglyceride, see a tremendous storage of carbon, hydrogen, and oxygen, because that's what it's all about. And they're pretty big. Now, there's a couple of different types you've probably heard about with 2 flavors of fats that you want to be in the forefront of your mind. Now, there's animal fats and there's plant fats, and we hear a lot about what you should be consuming. Now, animal fats, like for example, when I was just a little kid, my grandma would save the bacon fat. Now, it was liquid when it was warm, but of course it becomes a solid at room temperature. And you always wonder about that. Geez, do I want this stuff floating around in my arteries? Well, the good news is we're 97 degrees Fahrenheit as an internal temperature. But that kind of fat itself, it tends to be a bit of an unhealthy fat. It's hard for our bodies processing them. You think about, is this going in at my arteries? Is it going to lead to hypertension, high blood pressure, and things like that? Well, the animal fats themselves are solid at room temperature because of a little bit of chemistry. Now, we tend to say that animal fats produce what are called, more properly defined as saturated fats. Now, saturated means that something has a lot of something in it. It's saturated by it. Well, what's it saturated by? It's saturated by hydrogen atoms. That's it. It's all about how much hydrogen it has. Let's look at the molecule. You won't see a double bond in anything. In fact, here is your saturated fat. So just going through it, every place that carbon can make a bond. Now remember that carbon is 4 steps away from the end of the periodic table. So when it covalently bonds, it will play sharesies with 4 neighbors. That's how it gets its bonds. And carbon likes to bond with hydrogen. Hydrogen is perfect. It always donates or shares 1 electron. So carbon's very happy to do that. Carbon can share with an adjacent carbon atom. That'll totally work. But in each case, if you look here, in this molecule portion right here, the hydrocarbon itself is saturated with hydrogen. So all you will see are single bonds. Okay, so that's a saturated fat. I mean, off the end, right, here's your glycerol, and your fatty acids here are absolutely saturated with hydrogen. Okay, I'm just going to draw around this portion. Okay, okay, and there's your fatty acids. So that tends to be what you see with bacon fat, and if you do butter, for example, make it from milk, yeah, solid at room temperature, totally get it. Plant oils are a little bit different, and it's often construed as better for you. If you look at canola oil, safflower oil, olive oil, right? Not all plant oils, of course, are liquid at room temperature. There are some that tend to be a little bit more solid, but they tend, by and large, to be unsaturated as far as their fatty acids go. So the hint is to look for double bonds. I mean, that's a dead giveaway. So when you go into the hydrocarbon area of the fatty acids, as soon as you see carbon playing double sharesies like that, you see that there's a huge amount of missing hydrogen, right? There's no hydrogen link there or there. Come on, stylus, keep up with me. There, there, there. And that's because carbon is sort of double sharing with its neighbor. And what this tends to lead to, I think I missed one. There we go. Missed a couple. I think I got them now. This leads to a lipid, which will be, like canola, will be a liquid at room temperature. Healthier for you. The animal fats, they're often more associated with what we call hardening of the arteries or atherosclerotic plaques. Say that one 5 times fast. And that's not healthy, right? Leads to a narrowing of the arteries and increases your blood pressure. But fat is, aside from whether or not we're looking at saturated or unsaturated fat, fats themselves are just incredible energy storage. Now, this is kind of interesting. This is a little histology lab slide. And what you're looking at are fat cells. But I don't think you've ever really looked closely enough to see where the fat is actually stored. Let's go with purple here. Now, this is, when you look at the cell, it's pretty easy to find, for example, the nucleus. That's not hard at all. But when you look at the rest of the cell, you look closely, you're like, what the heck is that all under the cell membrane? Well, those are lipids. So our fatty tissue, which is a kind of connective tissue, swells out kind of like a balloon. So this can lead to yo-yo dieting, where you go on a diet, you lose a whole bunch of weight, and these cells shrivel up. Right? The baggie becomes less full of lipid. Think of it that way. And go off the diet, overconsume, drinking, eating, otherwise, and these cells will fill up again. And because they take up space, right, they have volume, you'll have what's called sort of a yo-yo weight gain. We're meant to store fat. Our bodies are loath to get rid of it because it's such a great energy source. Our bodies will run primarily off carbohydrates, and then our bodies will start looking to the lipids as an energy source because they're sort of important. They tend to hoard them a little bit. Now, remember how I said fats were neutral, right? Oil floats on water, wants nothing to do with water. Well, Mother Nature always finds a way. You see, our cell membrane itself is sort of a hybrid. You notice something's missing on this molecule. Now you'll say, hey, where did the third fatty acid molecule go? Where the heck is that? Why are there only two? And why is phosphate sticking out on the side? Well, in our cell membrane, our cells need a little bit more flexibility. Our cells need to associate with water in a way that allows a sort of a differentiation of the inside and the outside of the cell. So we have to let fat fear water because it's hydrophobic, right? That's what fats are. That's why we say they're neutral. Yet we need a part of the fat that likes water. Now, where I'm going with this is in how the cell membrane is set up. So I'll sort of personify Mother Nature. By fitting in this phosphate group, PO4, now think about phosphate for a second. It's got a 3- charge, negative valence. And you say, wow, like a negative charge might be something that a water molecule would find very attractive. So I'll draw negatives on this. And if you think about that, your garden variety water molecule, which is a dipole, your hydrogens are going to be attracted. I'll just write it like this. There we go. Your hydrogens will be attracted to that. So now what we've got by putting a phosphate group with glycerol in place of one fatty acid is something that can interact with water and part of the molecule that doesn't like water. So this side is water loving. And this side doesn't want anything to do with water because it doesn't have any charged ends. So it will face away from it. And that makes for a very interesting molecule. The way it's drawn is like this. A little squiggly there. I sort of draw the glycerol and the phosphate group together there. And the fatty acid tails are sort of drawn on this side. Now, oil, you can mix oil with oil. It's okay with that. The oil particles will come together. But the oil particles really won't want anything to do with fat. So what you see is you have a charged end, and in here, this is neutral. Now that leads to some pretty interesting biological makeup. It's going to pop onto the next slide. This is a formal way of showing it. There's quite a bit here when you look at the phospholipid structure. Not to get too confused, just focus in on that right there. There's your phospholipid head. There's a little bit more to it, but I wanted to show you the official molecule. Okay? Now the polar heads, let's go ahead and redraw that. This is the polar head, and here are your fatty acid tails. You get really two regions of a molecule that will interact sort of differently. And it's interesting now because instead of just carbon, hydrogen, and oxygen, we've introduced a little bit of phosphate. So we've kind of got a specialized triglyceride here. And it's really good at forming membranes. In fact, it's a big part of soap. You probably never thought about how soap works, but if you think about it for a moment, isn't soap one of the things you can use to make soap is animal fat? It's interesting. Well, okay, animal fat. Why would fat wash away water? Oh, wait a minute. It's not just animal fat. It's animal fat with, well, that has incorporated elements into it to make it not just fat, but to make it phospholipids. So it's a specialized kind of triglyceride. And when you wash your hands under the water, water is attracted to that phosphate head, or polar head, I guess I should say more formally, and water will drag away the phospholipid and any dirt that's associated with it. But more on that later. Okay, so now you've got a sort of a nice version of the molecule sort of laid out this way. So you can see the polar head, which is water loving or hydrophilic, and now you can see the tails, which are not so interested in water because they have no charged side groups. So they're hydrophobic. That means that the tails will do their best to face away from the water. They want nothing to do with it. This molecule will flip depending on how it's situated in water. Really comes down to the fact that phospholipids are the backbone of cell membranes. And it's phospholipids themselves, because of their chemistry, will automatically create a membrane. So I'm going to sort of draw this and sort of show you without purple. Let's skip it on purple this time. If you had a whole bunch of, let's say we had a whole bunch of phospholipid monomers. So let's say we have them, let's say we have them sort of facing every which way. So there's the fatty acid tails. There we go. Say we go like this, and like this. Now, I won't draw all of them, but you'll get the idea. They won't stay this way. They won't. If they're in the presence of water, drawing some water molecules here. They'll line up in a way where the phosphate heads point towards the water and the tails will just point away from it. So what would happen in sort of that ensuing result is you would get the formation of a membrane. Now this will just be a simplified drawing. And I just need, for the purposes of illustration, understand there would be a lot of phospholipids. So I'll use more than I have in the above drawing. So we'll go like this. Now the first thing that will happen is that the phospholipid tails will sort of rally the wagons because they want nothing to do with water, but they'll have everything to do with each other, right? Neutral loves neutral. So the neutral tails, the fatty acid tails, will face in towards the middle. And this makes, think of it almost as like a fatty layer. Now the water, we'll assume that the water, we don't have to assume, the water is going to align directly with the polar heads, like that. Now what this will do, if you have enough of these phospholipid monomers, what you'll get is you'll get a completely circular arrangement where it will look like this. And water will be on the outside like this. Draw this a little bit bigger. Just want to go back to a dark color. Keep the theme going here.
And on the inside, you'll have water, like in the cytoplasm in this region here. Didn't pick up that dark color, so I'll get it now. So you would have water on the inside, there we go, of the membrane in this location. Now what that does is it ensures that the polar heads are facing out towards water, while the tails face away from that. So water can be on the inside or the outside, and it's largely due to the fact that the phosphate heads are charged, and they're okay with interacting with water, but they are not okay in interacting, the fatty acid tails are not okay interacting with water. So the phosphate heads will point towards it, and the fatty acid tails will not. They're neutral. Think of them as oil. They don't mix with water. So we get a spontaneous bilayer forming. Now this graphic was set up to sort of demonstrate that. When you look at emulsification with soap, the reason why soap is so effective at taking things off your hands is that the polar heads will interact with water like this, and the dirt or grime that is in the center, with dirt tends to be sort of neutrally charged. So does grime. Think of having oil on your hands, etc. So the oil on your hands goes in with the fatty acid tails in here. There we go. So oil and dirt and grime will be captured in the center, and literally the water on the outside will drag the phosphate heads away. So it drags everything down the drain. And that's why we call water the universal solvent, because it can interact with a lot of things. And in this case, it interacts with the phosphate heads. And because you've had emulsification, it drags the grime and dirt away with it. That's pretty cool. So the point we're trying to make here is that those soap bubbles that you see every day when you wash your hands are roughly equivalent to a cell membrane. They're both phospholipid layers. So we're trying to impress this on you by showing you the phospholipid bilayer here, typical cell skin, if you will, so that you sort of take this all in. So let's take it all in. A little bit more here, right? Talking about the polar ends. Let's see if I can switch this up, something a little more dynamic. So here's your polar ends here interacting with water, and polar ends here interacting with water. However, your interior, choose a nice sort of pinkish color and turn this region in here that I'm highlighting, this region, the fatty acid tails, they point towards each other because they're neutral, just like oil, right? They want nothing to do with water. And it explains why the plasma membrane assembles the way it does. So, you've got a molecule that's partly polar and partially neutral, and it's responsible for the creation of a cell membrane. Everyday miracle, I kid you not. Because this molecule can bind with water, and it can carry away the fats, we say it's a good emulsifier. That's exactly what soap is. It's the great emulsifier. And it breaks up, if you put a drop of soap into some oil, you'll see the oil break up into little, sort of like little droplets. And our bodies do this to digest fat. In fact, your liver produces a ton of bile to make this happen. So phospholipids are lipids, but they're sort of a special class, and we use, in particular, here it's called, it's called bile, and it comes down from your gallbladder, and it emulsifies fats in your digestive tract. If we didn't break all the fats in your body down, let's say your trip to Burger King, it's quite a good one, and you get these big globules of fat. And there's a great animation on the website. If you'd like to see one, go to the digestive system, and there's an animation there I suggest you check out. But in the meantime, We break those giant fat globules into little tiny bits. And this is much more effective. It increases the surface area so that your digestive tract has an opportunity to better absorb it. You can do this if you go home. Take a little bit of olive oil, take a little bit of soap, put it in something that's roughly like a test tube or a tall sort of thin glass or tall thin tube, whatever you have at home. And if you shake it up, what you'll see with a little bit of soap and a little bit of the oil is you'll see it break up into sort of this frothy mixture. And that's actually what happens in your small intestine when your liver sends down bile. So in a way, our liver sends down something that's kind of like soap, in a way, just in a way, to help us break down fats. Because we want to absorb all of it, so we have to break it into little tiny chunks, and that's more effective. Yay, emulsifiers. One more shot if you didn't have enough fun checking it out the first time. Now, there's a class of lipids we haven't talked about, and they're called steroids. When you see 4 fused carbon rings like this, emphasis, 4 fused carbon rings, in this nature, then you'll know you're either looking at steroids, you'll be looking at subclasses of steroids, and it's kind of a dead giveaway. Vitamin D, ladies and gentlemen, looks like this. Testosterone looks like this. Estrogen looks like this. It's a very interesting molecule. In fact, forms the basis of many of our hormones. You might be a little surprised to hear that cholesterol is a steroid, but it's this biological structure right here that is critical for life. Yes, you do need cholesterol. Now, if we zoom in on one particular form of cholesterol, known as testosterone, this is what gives males their muscle mass, which is on average 1/3 greater than females. Look at the side groups here. You'll see that methyl group there. There's a methyl group there. This is known as a hydroxyl group. Now that is what it looks like when you're looking at a steroid that has side groups sort of in this fashion. Okay, there's no fatty acid tails. We're looking at carbon rings, and they become sort of, well, these carbon rings can be multi-purpose hormones. Not trying to make you dizzy, but I have to show you estrogen. And here it is. Now, if you look at estrogen here, we'll give you a chance to take a visual on it for a second. You'll notice that some of the chemical side groups are very different. Okay, so you can see a methyl group and sort of a double bond to oxygen, a hydroxyl group down the lower left-hand corner. Now we'll pop out here, and you can see, they're similar but different. This is a significant enough of a difference to cause, if females injected this into their bodies, they would gain muscle mass, the jaw structure would grow and widen. It would cause the vocal cords to thicken, deepen the voice, right? There is a little bit of this in the female body, just not that much. Just like there's estrogen in male bodies, just not that much. So there you go. Steroids. Well, we've been speaking about lipids, fat, oils, and waxes. So ladies and gentlemen, here's your 4th class, your 4 fused carbon rings known as steroids. And yes, vitamin D looks like this. So you can see how important it is to consume sufficient amounts of vitamin D. Think of it as forming sort of a basis for raw materials for forming your cholesterol and your estrogen and your testosterone. We need steroids, and we do in fact consume plant steroids all the time. A lot of things that we consume just get rearranged. Case in point, cholesterol from foods we eat, vitamin D from foods we eat. You get it. Now we'll finish off the last little bit here talking about androgens. Now andro basically means male, and anabolic means to build up. I always think of a sort of a large person named Anna, right, taking these steroids. That wouldn't be a good thing, but anabolic means to build up. And if males take anabolic steroids, they can of course get sort of enhanced male characteristics. But some side effects can be pretty bad. For example, you can see there where it's talking about, let's see if I can pull this down a little bit, shrunken testicles, some female breast characteristics, some balding, some sort of cystic acne. This stuff isn't good. It's also hard on your liver, tough on your prostate. And in males, sort of in the pursuit of this sort of male Adonis look, you know, that wide shoulders, thin hips, six-pack abs, really what you have is you have too much of the male androgen, and it's essentially poisoning the body. It can actually have the reverse effect on male sexual performance, shrinking the testicles. This doesn't lead to anything good, folks. Now, these kind of things can be taken orally. They can also be injected. The brutal irony is that the people who are afraid of needles, well, if you take this stuff orally, it's even more toxic on your liver. It's extremely toxic. Injections, not advised, not as toxic, but you're really on sort of a failing path. It's not good. In the pursuit of male body image, you're not really getting anywhere. And here's everything you can get. Liver cancer, depression, because you've got excess male androgens in your body, hostility, aggression. It's not worth it. So the risk of HIV, which they're referring to down here, what they're speaking about, and I'll just highlight that, is sharing needles. HIV is an opportunistic virus. It really wants to get into your bloodstream because it infects immune cells. So it's vital not to go down this road, because if there's any contamination or blood contaminants, you could run the risk of the human immunodeficiency virus, which leads to AIDS, which is where you can't fight infections very well. And the common cold becomes a lethal thing. Not good. So the pursuit of body image, ladies and gentlemen, is not worth it. And when it comes down to it, we look at this material right here. Oops, there it is. The 4 fused carbon rings that make up this cholesterol, as I'm highlighting here, these 4 fused carbon rings are the same ones that make your estrogen, your vitamin D, etc. They have a function. We do need cholesterol. It gives integrity to the cell membrane. That's not the problem. The problem is when we consume too much of this. Excess cholesterol can cause something called atherosclerosis. Atherosclerosis. There you go. And what it means is hardening of the arteries. Now, this isn't something I worried about when I was younger. Sclero is Latin for hard, so I'm just making a connection for you. And if you're consuming too many of these, too much cholesterol, too much fat, the possibility is that you can get cholesterol building up in your pipes, right, in your blood vessels. And it forms something that we call a plaque, which isn't really what you want. So in the next slide, you can see the buildup right here. I'll just highlight it. And what it does is it occludes. That means it begins to cut off the lumen. The lumen is the space that a normal artery would have for the passage of blood. So atherosclerotic plaques cut off the flow. To make matters worse, they can even dislodge and form what's called an embolism or a blockage. Think of it as sort of like a dam that won't let anything through. And that can, if that happens in the blood vessels of your heart, you will be experiencing a heart attack. It's not just the cholesterol that's the problem, folks. It's calcium. Um, think of it as becoming a really hard cholesterol material. That's not good. And it will occlude the blood vessel, and that will cause issues like this. So the lumen is this region right here, so I'll put an L. And it should be open up wide, but you've got all this schmutz on the outside right here, which is your cholesterol, and it's beginning to narrow the pipe. And as the pipe narrows, what you'll get is you will get a rise in blood pressure. So there's medications for these things. You might have heard of them. You've heard of probably of statins, is what they call them. Lipitor is just one. Crestor is another. To reduce in your body, it's your liver that's really to blame for this. Diet is 30%, but your liver, especially at nighttime, will produce a lot of cholesterol. And there's a couple of different types. There's low density cholesterol, which is bad because it builds up in your pipes the worst. And then there's your friendly cholesterol, your high density cholesterol, which has sort of the counteractive effect. It's pretty good at scrubbing your pipes, your blood vessels through. If your low density numbers are too high, your doctor will worry that your blood vessels are starting to become plugged up. And that could potentially lead to an occlusion, which could lead to a heart attack. In this case, the vessel has become completely occluded. There's no way through. This blood vessel here is quite occluded. It's a pretty major concern. This would show up probably in blood pressure readings. You would normally be 120 over 80. You might have heard of that. We'll talk about it later. Extreme blood vessel occlusion. You start to see your numbers creep up in the 140 range, over 95 or above, and you start to see that the pressure is building up. That's not a good thing. Now, there are some good fats out there. This is the kind of fat that you probably haven't heard of. It's when you look at fat cells and they're completely and amazingly populated with these little guys. You remember these guys, mitochondria. And you say, well, what the heck is, why are there so many mitochondria in this fat cell? Well, this is a very juvenile fat cell. You're born with quite a few of these, and it's called brown fat. And if you get a lot of mitochondria, it's the mitochondria, they're a little bit red. But if you get a lot of them, then you'll kind of get this sort of reddish-brown appearance. Enough to sort of look at it and say, hey, that fat looks brown. Now, you're born with this. It's interesting because you always talk about your birth weight and your birth chubbiness, and it's okay, babies are cute. Everybody was cute when they were born. But this kind of fat is found in some very temperature-sensitive regions. For example, I'm circling the kidneys right now. Right now, I'm circling the spine, the base of the neck. Here, obviously, is the heart. Now, if you think about fat as an energy source, it can produce a lot of heat. Now, if I was Mother Nature, I'd be thinking right now that I should be insulating these really important regions of these newborns. Well, brown fat is a kind of fat that will burn to produce more sort of heat energy. And that heat energy helps to protect these vital regions of neonates. Okay, by neonates, I'm talking about babies. It is a very smart strategy. It's a special kind of fat that can keep these regions warm, and that is good for survival. Now, you don't retain a lot of this brown fat. It's a kind of fat that gets consumed to produce warmth. You have a lot less of this as you age. So we'll sort of finish, this is the last slide, by saying the leading cause of atherosclerosis, well, I would say the leading cause really is heredity. Heredity roughly is 70% of the enchilada. There's not much you can do about that. And the problem is your liver, especially at night, is cranking out a lot of cholesterol. So what's the solution? Well, you have 30% roughly, which is diet. Eat well. Bill Clinton adopted a vegan diet and has largely cleared out a lot of his cholesterol issues. Really convincing the liver to cool it is the reason why your parents and your grandparents will go on cholesterol medication. That's a smart strategy because the liver is overreacting and producing something that can plug up your pipes. But 30% is diet. If you increase your fiber, do the right things, and exercise, you can get that number down as well. So the moral of the story, look after yourself. If necessary, you need medication. Exercise, take care of your diet. Okay? Look after your parents, look after yourselves. All right, ladies and gentlemen, that's it. The new and revised version of Lipids is now done. Ciao and have a good one.